This is video 23 for College Algebra. Today we're going to be looking at logarithms and exponentials. So first of all, an exponential function is some base to the power of x. So think exponential exponent is x, all right? Now our base has to be greater than 0 and it cannot be 1. So for an example, we've got f of x equaling 2 to the x. All right, we can make a table. We can do that just by plugging in values, or we can look at our graphing calculator or Desmos. Okay, this is what our function looks like, and we've got an asymptote at y equals 0. So we've got kind of like a wall that this function cannot pass through. All right, now solving exponentials, we can solve this using the one-to-one property. So first of all, we need to have the same base, and then we can set our exponents equal and we can solve. So for this, I've got a 9 and a 3. Now clearly those aren't the same base, but I can rewrite 9 as 3 squared. All right, and so now I've got the same base. I haven't really changed any numbers, I just changed the way they look. Okay, so 3 squared is still 9. Now I can put my exponents equal. 2 equals x plus 1, and so x equals 1. All right, this next one, a little trickier. First of all, we've got a fraction in here, so that's a little different. If we've got a fraction, that's the same thing as writing 2 to the negative first, and then to the power of x. And then I can rewrite 8 as 2 to the third, 2 times 2 times 2. All right, so this is actually 2 to the negative x. So I'm going to go ahead and put our exponents equal. So we've got negative x equaling 3. So that means that x equals negative 3. All right, a couple applications. We've got compound interest. You might have seen this before. If not, A is our total. It's our total amount. P is our initial amount. Sometimes people call that principal. N, right here, N is the number of times compounded in a year. So the number of times we collect interest. If we were collecting interest quarterly, then our N would be 4. If we were doing it monthly, then N would be 12. And our R is our rate, and we need to convert that rate to a decimal. Okay, it might be 3%, so then we would change that to 0.03. And then T is time, and time's always in our, and so then we can also do this. We've got exponential growth and decay. This is where we would be compounding continuously, so when we were always collecting interest. So here we use E. E is not a variable here, it is a number, and it's about 2.7 and change. And you can find that in your calculator. And so we'd have all of our numbers stay the same though. A is our total, P is our initial amount, R is our rate, and T is time. Okay, so we've got basically the same formula for growth and decay, but with decay, our rate is negative. We could also say that these formulas are for when we are compounding continuously. All right, so if we do an example problem, we invest $12,000 at 3%. How much do we have after 5 years? So if we were compounding monthly, let's go ahead and write this out. We'd have 12,000, that's our initial amount, times 1 plus our rate, which is 0.03 over 12, since we're compounding 12 times a year, and then to the power of 12 times 5, since we're doing this for 5 years. All right, so the good thing is, once we get this into, once we get all the numbers into our formula, we can just plug all of that into our calculator. So if we plug that into our calculator, we get $13,000 900 and I believe it's 34.40. Now we can do the same with compounding continuously. Here we're going to use our other formula, this exponential growth and decay. So since we are growing our money, we're going to be using our exponential growth. And I did make a mistake here. This should be 13,939. All right, so for compounded continuously, we'd take 12,000 times e to the power of 12 times, I'm sorry, 0.03 times 5. So typing that into our calculator, we could take 12,000, and then here we've got this e with a little x, so we can say to the power of e times our rate times our time. All right, so this would be $13,942.01. So it's not much of a difference, but compounding continuously will get you more money. And if you do it over a long period of time, that adds up quite a bit. All right, with our transformations, these are the same as all of our other transformations with quadratics, absolute value. They're kind of the same thing. So our a value in the front is a vertical stretch. So it's going to make it taller or a lot longer vertically. If it's negative, it's going to flip over the x-axis. Okay. Our h value goes left to right. It's a liar. So if it says +5, we're actually going to move 5 in the direction of negative. And our k value moves up and down, and that tells the truth. Okay. And we'll get to this here in 1 second. Now a logarithm is another way, is the inverse of exponentials. So if I've got y equals log base b of x, so that's how we say that's a base of whatever this number is. Okay, if I were to rewrite that as an exponential, this is how it would look. B to the power of y equals x. So logarithms always equal exponents, and that's something that's really important for us to remember. Now, if we shift gears going back to transformations with our logs, we have the exact same transformations. They do the same things. This time, it's just kind of rewritten to a logarithm. And remember, our h value is a liar. It moves left and right. Our k value is up and down, and our a value will flip it over the x-axis. All right, looking at our properties for logarithms, if we have a log base a of 1 equaling, that will always equal 0 because a to the 0 power equals 1. Okay, log base a of a always equals 1 because a to the first power equals a. All right, and you guys can see our next two rules here. The last one's kind of goes hand in hand with when we solve those exponential problems with the same base. Here, if we have the same base, we can put these part right here equal to each other. So if I've got log base a of x equals log base a of y, then I know that x equals y. Okay. If you see a natural log, so ln, you might see that on your calculator above or near your logarithm. That just means we have a base of e. Okay. And using your graphing calculator, you can either hit alpha window 5 or you can hit math up if you need to type a logarithm into your calculator. Okay, a couple examples. Log base 4 of 1, well, that says 4 to what power equals 1? That would mean x equals 0. Okay. If we've got a coefficient in front, we can pop that back as a exponent. So this would mean 6 to what power equals 20 to the 6th power. All right, that would be x equals 10.03, and something like that is something we can type into our calculator. And then the last one, we've got the same basis, so then I can say x equals 12. All right, so that is just kind of our introduction to logarithms and exponentials. We've talked about how to solve a little bit, some transformations, and some applications.